G'day lads, lasses, everyone. How you going? This video's taken a while to get things organised, get things on the board. I hope you can appreciate the time I've put into this. But anyway, let's get into the video. So this video is going to be on switchboard testing, but also testing the rest of the installation. I have set up a very basic installation here. We have got a makeshift main earth. We've got our mains up there. Coming out here, we've got one socket circuit and one lighting circuit. Just really basic, but from the principles in this video, you'll be able to understand how to test an installation properly and how to test it to the current wiring rules we have. Moving on from that, the test equipment I have here is I've got a Klein Tools CL800 clamp meter and then a Mega MFT 1825. So before you look at the switchboard and go, oh, this Sparky Dave's a bellend, he's done it all wrong. What you're looking at here is an installation that I've set up purposely for this video. I have set a couple of faults up just so we can go through the correct testing procedure and identify these faults. And there's a couple of common ones and a couple of things I've intentionally put in here so you guys new to the industry can learn and see and hopefully not make these basic mistakes in the field. Before we get into it, go and slam a like on the Instagram. I'm going to put together something for one or two of yous to be able to win. Hopefully give something back. You guys have been awesome and the support's been awesome. Big shout out to big boy Luke. He knows who he is. And yeah, let's crack into it. So over to the side here, I've got a couple of RCBOs. Now these are residual current devices with overcurrent protection. So they work as an RCD and as a circuit breaker all in one. This one here is a 2-pole. And this one here is a 1-pole. As you can see, it just takes up one slot. I will be wiring one of these into the switchboard when I remove some of these components for our live testing after. So the first things you want to go looking at in the switchboard are purely visual and mechanical things. So things to look out for are your bare conductors hanging out of these terminals. What you want to do is have the insulation flush up to the plastic here. Not so that the clamp is touching the insulation, but very similar to this one. That one there is good, this one there is not. So what we'll do is we'll pull that out, we'll trim it down, and we'll clamp it back in there so the insulation is flush with the edge of that. The next thing on here is this phase bar, bus bar. So if you have a look at this, the plastic shield or insulation on it has been cut too short. So what we'll have to do is cut a new one of these and put it on. You'll find you'll probably have to take the whole thing out and start again. And looking further down, sometimes you'll come across where circuit breakers and RCDs are different sizes, such as this Voltex brand. The phase bar actually sticks out too far, way too far. And the other thing is, if you try and line them up, you're going to have a hard time putting the cover on because these aren't going to line up properly. So don't even try doing that. Throw a wee bit of 6mm between the load side of the RCD and the first circuit breaker and then run this bar across from there. So the next thing is the main earth label here. I believe that everyone should be putting them on switchboards. You always get a Sparky out there who says it's not required or it's not legislation, but it's just the same as saying putting a socket on the wall on the piss and just saying that, oh, that's not legislation to make sure they're level. Don't be lazy, just throw them on. They actually come with the switchboard as well. The next thing we want to look at is the characteristics of the RCDs and their loadings to make sure they are compliant. Maximum demand actually says that the sub-circuits must be equal to or less than the maximum current rating of the RCD. So 2 16s and a 6, well 3 6s are 18 plus 20 is 38 amp is the maximum current capacity of these. So on a 40 amp RCD, that's fine. Over here we've got a 40 amp RCD, we've got 2 16s and a 10, and that's 42 amps. So that is too much loading for this 40 amp RCD. So all you'd have to do is just pick up a 63 amp RCD. It's the next available size up. So the next thing, we've got to look at the rating. These are both 30 milliamp, it specifies it there, and 0.03 amp there. So the 30 milliamp rated RCDs are the standard ones we put in residential. So if you have a close look, you can see in this wee square box here, these are type A RCDs. So as you would have seen in the wee box, it had a sinusoidal AC waveform and also a DC, pulsating DC fault current waveform. Now in New Zealand, these are required. In Australia, you can have type AC RCDs, which just have the sinusoidal waveform in the box. So the type AC RCDs are suitable for most appliances anyway. Yeah, in New Zealand, with the pulsating DC, that protects the RCD from loads that have rectifier diodes or thyristors that have stuffed out and caused an issue. This Vinkier circuit breaker, these ones here, if you see them in the field and you don't have to touch them, don't touch them. As soon as you activate them, you can struggle to turn them back on, just like so. So we tend to get rid of them. If you get lucky and somehow manage to turn it on and then it decides to spring down, you will get a callback and you'll have to go back there and replace it anyway. So along with fixing these two faults that I've seen, I'm going to get rid of this whole bunch entirely. It's no longer needed for this video, and I'll throw this RCBO in its place. Sweet as. So what I've done there, just replace that bar, put that neutral in properly, and then change that block out for the RCBO. Wicked. When you throw these in, make sure you crank them up a bit with a big flat head or a proper circuit breaker screwdriver, not just a posi or small flat head. Now what we want to go around and check is that every single terminal is tight and done up properly. Nice. Looks like we've got a loose terminal here. So tighten that one up. Then we get our big flat head and crank it up a wee bit. Just go through the whole lot. Cool, they're perfect. And then you can also go around and do a quick pull test on all of the conductors. Make sure that nothing's coming loose or falling out. And we're good. I've come across so many of these terminals that people have forgotten to tighten up. They've created hot spots on the circuit breakers over time and melted and welded things together, which could have caused fires. So make sure you do that. Sweet, so now we get on to mandatory testing. So the first things in the system that we want to test is the main earthing conductor continuity. So between the earth stake and the earth bar there. Obviously, the switchboard and the main earth are going to be quite a fair distance away from each other. Not like in this video where I've got the liberty of having the main earth right next to the main earth bar, so I can easily just test between the two using the meter leads. It's not going to be like that in practicality. Throw the meter onto ohms, take it off continuity, and put it on ohms measurement, and we're going to test, firstly, put the leads together and see what the resistance is. So we've got 0.1 ohm. We're going to subtract that from our measurement we take between the earth bar and the earth stake. So what we're going to do here is test from the earth clamp back to the main earth bar. So our result was 0.01 ohm, which was the same resistance in these leads. So it's negligible how much resistance is actually in this cable. Obviously less than 0.1 ohm, which is perfect. So the minimum resistance on any earthing conductor or equipotential bond is 0.5 ohms. So a result less than that is perfectly acceptable. A result more than that and you'll want to fix something. If you had an open loop between the main earthing conductor and the earth bar, check the terminations, check that the clamp's on properly, and check that a builder hasn't cut the cable on you. So you might want to check between both sides of the clamp to make sure there's minimal resistance between them, and make sure that you haven't clamped onto the insulation of the cable instead of the copper conductors. Moving on. So the next test in the sequence of tests is doing your equipotential bonding. Along with equipotential bonding is also the other earthing conductors. Now that's the only thing I don't have set up. I could have used one of these RCD bars as an equipotential bond, but it's the same process. Just test between the two or wherever that bonding point is and ensure the resistance is less than 0.5 ohms. Now the next test, we want to do an insulation resistance test. So what you'll need for that is a multifunction tester and a couple of leads plugged into it. Now when we do our insulation resistance test, you'll see on the mega here, it's just simply turning the dial to these red indicators. Now we need to stress the cables at 500 volts DC. The easiest way to do this is to turn all of the circuits on, including your switches, and then we're going to directly short out on the end of our line connection out in the meter box. So I've set this wee connection up just so I can simulate having this installation live and going through the live testing for you guys. This connection here would be in the meter box. Of course, this earth here is going to be our actual earthing conductor, our main earthing conductor. The other one that we've tested for the installation is just a dummy. But what we want to do is put a dead short between neutral and phase. Now one thing I hadn't mentioned yet was the size of the conductors. Here we've got 16mm neutral screen with a 6mm copper conductor. There is table 5.1, which you need to go by if you're using different sized mains to ensure you've got the right sized earthing conductor. Now these three tests so far are all tests that have been done without electricity turned on. You don't want to be doing these when the installation's live. You want to have verified that everything's okay to liven first. What I'm going to do first is just test to ensure that these two terminals are definitely shorted out, and as you can see we've got 0.01 ohm. We've got this installation to do a test on. Just keep in mind that if you're throwing 500 volts DC down the load side of the circuits, there is some electrical equipment that can get fried, such as dimmers and some alarm systems. So make sure you disconnect those before doing this test. Now the next thing we do is we get rid of this MEN link, just unplug it for now, because now that we've shorted out the phase and the neutral on the line side, we've got a complete circuit between the neutral bar all the way through all of the phases and through all of these breakers and RCDs, all the way out to the complete loads on the circuits. Before you start your insulation resistance test, you want to do your first one on the leads of the meter to ensure they're not damaged at all, and you should be able to get a dead short. The result's perfect. Now you've verified these leads are perfectly fine to use to test the installation with. We're going to throw one of these onto the earth bar, the other one onto the neutral bar, and then we're going to hit the test button. And there we have it, greater than 999 mega ohms, which is the result we ideally are looking for. Of course, the requirement is greater than 1 mega ohm. If you are getting near 1 mega ohm, I suspect there's something you've got to look at. And what I would be doing then is checking the load side of the RCDs, checking the mains separately, and just making sure we can find out exactly what's causing the low readings. But once you're happy with that, everything's good, we can now get rid of that link over there. When you are doing this insulation resistance test, just make sure that you go all the way back to the end of the line side to do the crossover, because if you're going to shortcut and do it at the switchboard, then you're not going to get your insulation resistance testing done on that mains cable, unless of course you're doing it separately. Once you're done, throw your MEN link back in as well. And the next tests we're going to run through are polarity tests. Now the first one we're going to do is on the line side mains. So from the meter box mains to the main switch here, we're just going to ensure that we've got the right polarities on the cables. Even though you can visually see it, it is a mandatory test to go through. So what we do for that, we can put it on continuity or on ohms and just check the resistance or check the continuity. We're going to make sure that the neutral over here goes back to the neutral bar. So we'll put these together, see what we're working with first. 0.7 ohms. These meter leads have had their day and they'll probably be getting binned next week. So with that in mind, just check the neutral goes back to the neutral bar. So we've got our 0.7 ohms there and nothing between that and phase. And then we check our phase. 0.7 ohms there. And of course nothing between phase and neutral. So that's our polarity tests done on the mains. The next one we'd run through is a sub-main polarity. There's no sub-mains running off this board, so we can skip that one on here. If you do have sub-mains, make sure you go through and verify that the polarity of those cables are correct. Sweet. So the last part of polarity testing is getting these load side of the circuits tested to make sure that the polarities are fine at your lights, at your sockets, and at your appliances that you've got running off the circuit breakers. What I've got are two tools for polarity testing. These ones I made myself. So the first one here, I've got known resistances between the 3 pins, and here they are on the camera. So this one here is for doing the socket circuits in a house, and it's really easy because you can just get someone you're working with or an apprentice go around, throw it in each circuit. As long as you have the RCDs in the off position, all of your socket circuits run off the RCDs, so you can leave the MEN link in for that. It's only the fixed load appliances you'll have to take that link out to test. I don't have any on this board today, but I'll run through obviously one socket circuit and one lighting circuit and show you how it's done. Although I'm going to be showing you today using this on the switchboard and testing at the downlight, in reality that doesn't happen, mainly because the rigs are more concerned with a shock hazard happening off a phase neutral transposition or metallic parts becoming live. There would be no shock hazard in a downlight should the phase neutral be transposed in it. The worst that would happen is it would stuff the driver, or if the earth was transposed, the fitting might not work. Now the other things that you should be testing with the likes of this is your fixed loads, so hot water cylinders, heaters, and other appliances that the standard socket doesn't actually fit into. The only light fitting types that the rigs would be concerned about are metallic ones or Edison screw fittings. Now you'd have to verify your neutral is on the outer side and the phase is right in that middle part of the Edison screw. Now this cable here is the same known resistances. I've got them on wee tags so I can tell if I do forget. It's probably blurry on the camera here. As you can see, red, black, green, phase neutral, earth. So I've made these nice and long. So if I am working on a bigger switchboard than this and the earth bar's down the bottom or the RCD neutrals are at the bottom, then I can go between the bars fairly easily. Alright, so the first polarity test we'll run through will be the socket one. Plug that in properly. Okay, so I've got my meter here. Throw it on resistance and double check. So we've got 0.2 at the moment. And what we'll do with this is we'll throw one on top of the load side of the circuit breaker going out to the socket. I know it's this one, but you just go across the tops of them all until you find the right one if you didn't know. Go from there to the RCD bar. And as you can see, we've got 8 kilo ohms. So phase to neutral, 8 kilo ohms. Phase to neutral, 8 kilo ohms. Next we'll do phase to earth. Here we've got 2 kilo ohms. And if you can see on the plug top over there, phase to earth is 2 kilo ohms. And then the last one is neutral to your RCD earth bar, and that's 10 kilo ohms. So that matches up with that. Now if you accidentally had the RCD turned on, you'll see it's dead short. And that's because this RCD neutral bar is running back through the RCD, through the MEN link to the earth bar. The other thing with this is you've got to make sure that the switch mech is turned on, or your results are going to be stuffed. So that's the first one shown, and it's pretty easy. It doesn't take too long to go around and verify all of the socket circuits. The next ones though are your lighting and appliances. So this next one, we've got our lighting circuit over here. So what I can do is turn it on, clip it onto the phase bar there, make sure it's not making contact with anything else. Obviously neutral onto the RCD neutral bar, and earth onto the earth bar. From here, turn the light switch on, we'll check the meter again, make sure it's zeroed, and we'll go between phase and neutral. Now we've got 8 kilo ohms, phase neutral, 8 kilo ohms. Go between phase and earth. We've got our 2 kilo ohms, verified on there, 2 kilo ohms, and then neutral and earth, 10 kilo ohms. It works well, it speeds the process up, and I highly recommend that you guys make them. Alright, sweet. So the final test before livening the installation is we're going to check the correct circuit connections. The regs want you to verify 3 things. The first one is short circuits. Well, I've already done the mega test, which rules pretty much all of that out. The next one is transposition. Now we've done our polarity tests, we've ruled that one out. And the last one is interconnection. So we don't want any cable coming off any particular breaker interconnected with a different breaker or different RCD, although that's going to throw up an RCD fault straight away if it was on a different RCD circuit. But in particular, we want to be testing and ensure that each circuit is separate. Now it's pretty easy on this one, there's only the 2 circuits. So I'll test between them just to show you guys. All you want to do is put your meter on continuity. It's going to beep. So make sure the breakers are turned off, or there's going to be continuity. And as soon as they're off, there's no continuity. Now you could go around, test the whole lot, make sure nothing interconnects. The other things with circuit connections that you want to verify that our circuits are the way we intended to wire them. So what I want to test here is that from the bottom of the main switch, we go to the line side, or the top of the RCD and the top of the RCBO. Okay, we can verify that on both of them. Now we want to test, there's no continuity there, so the main switch works. There's no continuity here, so the RCD works. No continuity, so the RCBO is working. The next one we'll do is we'll confirm that our load side of the RCD neutrals goes back to our RCD neutral bars, and the line side neutral goes back to the neutral bar. Cool, line side's done, load side. And we'll just test between all of the RCD neutral bars to make sure that none of them are interconnected somewhere. And then the last thing we'll want to confirm is that the MEN link is intact. Perfect. So now we are ready to liven. I'm happy that this installation's safe to liven. So before we plug her in, what we'll do, make sure everything's turned off. Now that it's plugged in, we'll verify that we've got 230 volts there. So earth to line side, we've got our 230, 240 volts. So now that we're happy, we've done our continuity checks, we know the phases go to the top of the RCDs, we know the neutrals are in place, we've done all our other tests, so we can, by all means, liven these circuits. Now, These two sub-circuits up here, I've got nothing running out of them. I'm not going to bother livening them. We're just going to liven the RCD and the RCBO next. And we're going to do our manual test. So we've verified the RCDs are functional. So I'm probably getting a wee bit carried away with these RCDs at the moment, but all of them are set up properly. One other test we can do to ensure polarity, so going back to polarity before we get any further with this live testing, is we could put a remote earth outside somewhere, run our trailing lead, fly lead out to it, and back to the board here, and we'd test between our remote earth and our known 230 volt source and ensure there's 230 volts between them, and then we'd test between our remote earth and our earth neutral bar, which has its own fixed main earth, and we'd ensure there's 0 volts between them. This test simply verifies the polarity is correct on the line side of the meter, so the street connection side of the installation is correct. The next test we're going to do is our earth fault loop impedance test. Now what we've got here on the Mega is it's this green area, and we've got our line to earth and line to neutral tests. We do both of these tests because a short circuit can happen between either potential. First of all, we'll throw it on to line to earth, and by default it comes up with our 3 lead low current tests. That's what the 3LO stands for. Now this test is specifically designed not to trip your RCDs, or to give you the best chance not to trip them. It's never guaranteed. So you'd use this test on the load side of your RCD circuit, so on your socket circuits, and then if you push the select button here, you can go between the other 2 lead tests on here. So there's 2 high and 2 low. First of all, the 2 lead high current tests you want to do on the line side of your RCDs in the switchboard. So we're going to be testing from the line side of the main switch to ensure that if there was a short circuit, all of the switchboard gear could stand up to the current that would be produced from it. The 2 high test is the most accurate one, but it's definitely going to trip your RCDs if you're throwing it on them, so it doesn't work. Now the next one is your 2 low, and you shouldn't really be using this test. What it's designed for is if you've only got phase earth available and you need to do a low current test somewhere. Now on here, flick it to line neutral. The only test available is your 2 lead high current test. So when we're doing these tests, we want to do one at the switchboard to ensure that the circuit protection is going to work under fault conditions, and then we do our second test at the furthest socket from the installation to ensure that the longest path has an impedance low enough to operate the circuit protection under fault conditions. So our first test here we'll be doing will be our 2 lead high current test, and we're going to go on the line side of the main switch there. We've got it on line to earth, so what we're going to want is to put one into the line and one into the earth of this. Here goes our earth lead, and we'll hook this one onto the earth bar, throw our red lead in, and put it on the line side of the main switch. And then we just simply push test. So this reading here that we've come up with is our impedance, and then the one above it is our prospective short circuit current. So that is just voltage over impedance, so 230 divided by 1.17 equals 196 amps. So this fault current produced is going to be high enough to trip the circuit protection. It's lower than that 6 kiloamp rating on the switch gear. Now with our impedance result, you want to go through and verify under table 8.1 whether or not your circuit protection is adequate to disconnect within 0.4 seconds. Just so you guys are aware, this installation plugged in to this cable, or the impedance reading is quite high. This lead I've got it running off is probably a good 50 meters from the main switchboard. It does go back through a DB into the main switchboard. MEN link in here is just for demonstration. As a distribution board, you would only have the MEN link in if it had a separate main earth, but that's expected because of our distance. So the next test we'll be doing is going to be our neutral. But we'll be doing our 2 lead high on the neutral. So we put this one on the neutral bar, change the setting to line to neutral, and we're ready to test. Exactly the same reading. I don't think the reading's going to get any better than that. Alright, so now we'll do our second test, and that's going to be from the farthest socket from the installation. Obviously this one's pretty close by. First of all, we'll do our line to earth test. Now this one here, because it's on the load side of the RCD, it will have to be your 3-lead low current test, which is default, and hit test. 1.11 ohms, 208 amps. Then we put it on line to neutral. Now line to neutral test is always your 2-lead high current test, because it's the most accurate and fastest test you'll be able to do. You can't change it. The high current test on the neutral is not going to trip your RCD. 1.05 ohms. So what I've got here is a socket that's much closer to the point of supply. So I'll just do one here to show you what sort of results we do expect. And there we go, that's a much lower impedance. It's much closer to the point of supply. And of course there's a higher prospective fault current that's going to be produced. Alrighty, so the next lot of tests are going to be our RCD tests. For these, we use these yellow areas on the multifunction tester. The first one you want to set is your RCD milliamp ratings. Now we've already verified that our RCD and our RCBO are both 30 milliamps. So we'll turn this dial to the 30 milliamp dial, and then we're going to run through these tests one by one. So our test here at half the rated current, so 15 milliamps, we expect that these two units will not trip at all. Otherwise they are defective. At 1 times the current, we expect that these will operate under 300 milliseconds. Then we're going to do the 5 times test, which we expect these two to operate under 40 milliseconds. So when you fire the RCD tests on, you'll notice a wee angle come up on here. Now you can switch between 0 degrees and 180 degrees. What these angles are the 2 half cycles of your sinusoidal wave. So at 0 degrees here, you're going up on the positive cycle of the wave. And then at 180, you're now dipping into the negative side. You want to be testing each RCD test at both 0 and 180 degrees to get a proper test. For this video, to save time, I'm only going to be doing these tests once for the RCD and once for the RCBO, so once per unit, but only at the 0 degrees function, which is default. So I won't be doing the 180s. The first test we're going to do is our half trip. Put our earth on the earth bar, neutral on the load side. So we're going load side of the RCDs here. So the first RCD we're testing is this one here. And then with the probe, we go on our load side phase and we'll hit the test button. No trip. Do the same for the RCBO. No trip. So now we'll do our 1 times fault current. So this is throwing 30 milliamps down. And what we want to see here is that these RCDs operate within 300 milliseconds. So 8.9 milliseconds, that's pretty damn fast. We'll do the next test on it, which is our 5 times. So you generally expect a faster result, which we do, 6.89 milliseconds. So now we'll go through 1 times. 45 milliseconds, that's good. Obviously nowhere near as good as this RCD. 5 times, 8.98, exactly the same as 1 times fault current on that one. That wraps the RCD testing up. Last of all, we can just turn the downlight on. Sure it still goes for all you guys who haven't measured them before with 500 volts. Oh, and by the way, subscribe. Go to my Instagram, get on it. That wraps the video up. I know it's been a really long one, and thanks for watching it. Bloody good to get you guys on board. Make sure you subscribe, and make sure you watch my other videos. There's heaps of information out there. Cheers guys and girls for watching. You're bloody awesome. Rock on.